Hello, in this video we will be looking at how to determine the specific heat capacity. How do we calculate the specific heat capacity by experiment of water? Okay, it could be other materials, but we look at how it's found in water. Okay, now to do that, we need to look at the equations we use. The first equation, as from the earlier thing, is that the energy transferred Q is equal to the mass times the specific heat capacity times the change in temperature. Now we've got to be careful that if we use kilograms, we must use specific heat capacity in joules per kilogram degree C. If we use grams, we must use the specific heat capacity in grams, in joules per gram degree C. Anyway, that will come out in the mathematics. So that's one equation we need to use. But we also need to use how do we supply this energy. Now, the way the energy is easily supplied, at least in physics, is by the means of a heater. So let me draw a quick diagram of a heater. So here we have positive terminal and negative terminal. We'll have ourselves an ammeter to measure the current. Then we'll have our heater here. So this is our heater, okay, and then let's come back. So this is, if you like, a heater in circuit, and let's put a voltmeter across the heater. So here we have a heater. Okay. Now, heater there. So, well, how do we work out what energy that the heater is supplying? Now, the equation that we can use for this is we have, first of all, we got the power of the heater. P for power is equal to the current in amps multiplied by the voltage. So we can find out the power by measuring the voltage across there and multiply it by the current through this circuit. Now, what else do we need? Well, we need to know how long it's been switched on for. That will give us the total energy, because the electrical energy, which is transferred into heat, the electrical energy is equal to power times time, and the time must be in seconds. So we have current in amps, voltage or potential drop in volts, and time in seconds. So altogether, you see that the electrical energy supplied is simply equal to the current times the voltage times the time. And of course, what's going to happen is that their E is going to be equivalent to there. So we'll find that, in fact, therefore Q equals mc theta eventually will be equal to I, current, times voltage times time when we start applying the energy into the water. Okay, now we'll go and look at that now. We'll go and look at this equation and why that happens. So I shall rub this off now, and I'll draw the circuit again, but I'll draw it in water. So here we have our container, but an insulated container full of water, and in here, let's say we'll have our heater. This is our heater, and it's full of water, so the heater is, oh, we're missing some there, so let's have some water above the top as well. So here's our water, there's our heater. Okay, it's insulated, so we don't want too much energy escaping, and there's a lid there to stop the energy escaping, so it's insulated. Otherwise, we'd lose all our energy to the outside. And this heater here, okay, is connected via an ammeter to a power supply, positive, negative, and then back through to our heater. And we need to have in here, across the heater, we need to put a voltmeter, like that. We also need a clock, stopwatch, etc., etc., to time how long the heater's been on. So we are transferring energy from here into there. So going back to the previous screen, we have energy transferred is equal to mc delta T, changing temperature. Of course, I use another colour. We also need in there, we need here a thermometer to measure the raise in temperature. So we need a thermometer, and of course, to find out the mass of water, we have to measure the mass, or simply find its volume and calculate the mass from its density. So here we have energy transferred from the heater into the water equals mass of water times the specific heat capacity of water times the change in temperature. Now, as from before, we're going to, because of the electrical energy is equal to IV times time, we'll find we can replace this with IVT is equal to MC delta change in temperature. And then what we're looking for the specific heat capacity of water, and the specific heat capacity of water is C here. So we want to write that in terms of C, so therefore we can write that as the specific heat capacity is equal to current times voltage times time divided by the mass times the change in temperature. And that is in the units of specific capacity will be, if we measure the mass in kilograms, we'll get the units will be joules per kilogram, and change in temperature degrees C. So that's experimentally how we will find the specific heat capacity. There you go, and it won't be exactly the value we require, because we're looking for 4,200. We won't get that because there's bound to be some losses due to heat losses.